So today let's discuss the electricity topic. Last two classes we discussed about magnetism and simple harmonic motions as well as sound. Some of the topics, selected topics, I'm choosing here, right? So now I'm interested to discuss today the electricity topic, current electricity. So the basic theory of the current electricity has been evolved from the Ohm's law. So George Simon Ohm, a scientist name. Okay, so let me increase the screen size. Okay, so is it clear now? Yeah, first we'll discuss the Ohm's law, its formula, ohmic and non-ohmic conductors, examples, resistance and specific resistance, and units, and similarly the temperature coefficient of resistance, as well as uh, yeah, it is enough now. uh, First of all, George Simon Ohm is most basic component of electricity are voltage, current, and resistance. These three components or parameters are the fundamental concepts to understand the concept of electricity, current electricity. And without this we cannot even guess the electricity part. Okay, take out my figure. So right, so it may take less data to download this, so that's why. And the thing is, Ohm's law shows a simple relation between these three quantities, children. So what are those quantities? Current, voltage, and resistance. So Ohm's law states that what he stated actually according to Ohm is the current through a conductor between 2 points is directly proportional to the voltage across the 2 points, right? And he also states sometimes, as in some books, the others prefers to write that at a constant temperature, the current passing through the conductor is directly proportional to the potential difference uh, in that conductor. Okay, it is directly proportional to potential difference. That means the current passing depends on the potential difference of that conductor, right? So mathematically I can represent this as a, or I can indicate that voltage is nothing but the product of current and resistance. Voltage is equal to the product of current and resistance. So here the current, children, the flow of charge is called current. So as the charges flow in a conductor by changing their potential difference from one end to cross sectional area to another cross sectional area, then naturally the current flows in opposite direction to their charge flow. That means if the charge flow is from the right side to left side, then current will flow from left to right. So in the sense, the current flowing will be in the direction of opposite to the flow of electrons. Okay, and what is a resistance, uh, and what is voltage? These three let me define. Voltage is nothing but the potential difference developed in that conductor. Okay, and then what is conductor? Conductor is nothing but the electrons which are free to move in any metal or a material. The free electron contained materials comes under the component of conductor. So that means the current conducts in it, the current passes through it. So many, some materials are there which cannot pass the current. So if it takes a non-conductor example, just like a wood or cement or a, right, so there we don't find the passage of current. But in case of conductors, the electrons are very free and they are mobile. Now what is resistance? So what does it, how do we define the resistance? Resistance is a mm, the inverse of conductance, I can say. Okay, the ratio of conductance, I can say, that is the resistance. That means the force which is opposing the flow of charge in a conductor. The force which opposes the flow of charge is called resistance. Okay, and voltage is the change in difference, potential difference in that conductor. Now mathematically, if I represent that voltage is equal to some current into resistance, that means V is equal to I into R. V stands for voltage here, I stands for current, and R stands for resistance. So here this figure you can see here, yeah, at a constant temperature, the current I on y axis, the current voltage on x axis. Okay, voltage is on x axis and current is on y axis. At constant temperature, what's happening there? So it's a showing the straight line, it's showing the straight line. And this law is one of the most basic laws of electricity. It helps to calculate the power, efficiency, current, voltage and resistance of an element of electrical circuit. So this figure, sometimes I can write that you draw the triangle, make it half into horizontal base, and the second horizontal part you divide again two parts. Then in the first triangle, the upward triangle, you write V, and the downward triangle which has been bisected, so you had divided it. So the beneath triangle you write I in the left box and R in the right box. Now I can write that V is equal to I into R, but I is equal to V by R, or R is equal to V by I. So most books you find this figure, a triangle divided by two parts, the lower part again divided vertically into two parts, and written all the three boxes with filled with V, I and R. Okay, so children, this is how we can understand the concept of uh, that means the relation between a voltage, current and resistance. So if you take I is equal to, the top one is a top triangle, you write V, upward figure, and divided by R. Automatically you will be seen in the third figure, that is down in the third box. Okay, or if you want to the relation related with the third box, R is equal to the first box V divided by the second box I, isn't it? So from this relation also, here this relation V is equal to IR stands a very suitable relation uh, for any solutions, any problems which you need, which you find the current or resistance. If two terms are being known, that means R and V is known, then you can find out the I, or sometimes V and I is known, you can find out the R by based on this relation, right? So you see this figure. Okay, in this figure, I and V. I is denoted on x axis, V is denoted on y axis, right? And omega is the flow of resistance in a conductor. Okay, this symbol stands for omega. Okay, right. Now, this law is one of the most basic law, children, of electricity. It helps to calculate the power, efficiency, current, voltage, and resistance as well of an element in an electric circuit. So, in any electric circuit, what are the parameters or the uh, components I can find by using this Ohm's law, means the power, efficiency, current, voltage, and resistance. Okay, so in the next okay, see this figure. Ohmic and non-ohmic conductors, ohmic conductors and non-ohmic conductors, a very simple definitions are there. So the conductors which follow the Ohm's law, okay, What is Ohm's law? V is equal to IR. The conductors which follow this V is equal to IR, this relation, then all these conductors are called ohmic conductors. If they does not follow these conductors, Ohm's law, then they are non-ohmic conductors. So examples for Ohm's law: the current is directly proportional to the potential difference, copper wire, metal, etc. The conductor which are do not follow Ohm's law: diode, semiconductor, filament, and bulb, etc. Okay. Now, right. So the conductors which follow Ohm's law are called ohmic conductors. The current is directly proportional to the potential difference according to Ohm's law. But at constant temperature, children, as the temperature changes, yeah, one more you have to remember this relation V is equal to IR. It is not uh, able to agree, or it is not, the statement is not agreeable at the um, uh, temperature differences. It has to be obeyed, it will be obeyed at only when the temperature is constant. If temperature is not constant, if temperature alters from the low to high or high to low, then in this situation V is equal to IR relation does not works. Okay. And it objects or it obstructs this statement. Okay, the violates. So it only agreed at a constant temperature. If the temperature alters, then the Ohm's law is not obeyed or agreed. Okay. So Ohm's law is obeyed only at a constant temperature. This is the condition. At constant temperature, the current passing through conductor is directly proportional to potential difference and inversely proportional to, okay, directly proportional to potential difference, or I can write V is equal to some I into R, where R is the resistance. And examples for ohmic conductors, children. So copper is a good conductor, copper wire. Metals, all metals, iron, steel, okay, uh, nickel. Okay, so these are all good ohmic conductors. What about non-ohmic conductors? The conductors which are do not follow Ohm's law. Example of non-conductor is diode, semiconductor, filament bulbs, etc. So diode, semiconductor, and filament bulbs, uh, yeah, semiconductor is a non-ohmic conductor, children, because the temperature alters their resistance and everything get difference. And a diode also, PN junction diode. Generally, PN junction is a P type and N type, all are semiconductors only, and the diode is formed with help of semiconductors. So that's why diode is a not ohmic, does not obeys the ohmic conditions, Ohm's law conditions. So that's why they are been classified into non-ohmic conductors, right? And the filament bulbs are glass, whatever you can. So I'll show this example. You can note it, right? Conductors which follow the Ohm's law, the current is directly proportional to potential difference. Copper wire, metal, and etc. are the examples for that. And the conductors which do not follow Ohm's law, V is equal to IR, are non-ohmic conductors. Diode, semiconductor, filament bulb, etc. These are all non-ohmic conductors, right? And resistance and specific resistance we have to know, and their units also. Resistance is an what is the resistance? The force which opposes the flow of current in an electric circuit is called resistance. So resistance uh, resistance is a measure of the opposition to current flow in a electric circuit. He has given here in this statement, because I have written the resistance and specific resistance and units also, but the word and units has been printed over it, so it is somewhat not clear. So I define here the resistance is a measure of the opposition to current flow in a electrical circuit. So resistance is measured in ohms, and it is symbolized by Greek letter omega. This is the omega, children, the symbol of omega. Ohms are named after Simon Ohm, George Simon Ohm. This omega is been named after George Simon Ohm's experiment or proposal. Yeah, this is the symbol here. You can see omega. Children, sorry, this is the omega. This symbol, uh, which is used to indicate the resistance, children. Right now, uh, specific resistance. Specific resistance is defined as the resistance offered for a unit length and unit cross sectional area when the known amount of voltage is applied. So, what is specific resistance? Specific resistance is defined as the resistance offered for unit length and its a unit cross sectional area when the known amount of voltage is applied. That means he says that for example, rho R is directly proportional to length. If the length increases, then automatically resistance also increases అని చెప్తాడు. Then resistance is directly proportional to length and inversely proportional to area. And I will also write that resistance R is equal to some rho into L by A, where rho is a specific resistance. Rho is studied as a specific resistance, and this rho is equal to resistance into area by length. I can write that specific resistance is equal to resistance into area by length. So that's why I define here specific resistance is defined as the resistance offered per a unit length and unit cross sectional area when the known amount of voltage is applied. So I repeat again the same. So resist, according to the derivation, I can derive that R is a directly proportional to length and R is also inversely proportional to area. Then R is equal to some rho into L by A. The rho is a resistance, so this resistance is equal to specific resistance or resistivity. Rho is denoted, the letter rho is denoted by specific resistance or resistivity. Then that rho is equal to area into length, sorry, resistance by length. So resistivity is equal to resistance into area by length. Now, the resistivity is a specific resistance of material. When we have a thick wire, the resistance decreases. If the wire is thick one, what happens? The resistance decreases. The resistance increases when the wire is thin, as the area of cross section is less. So if the area of cross section is less, then resistance increases. So when the length of the wire increases, the resistance also increases. When the length of the wire decreases, the resistance decreases as the length is less. So దీన్ని బట్టి మీకు ఏమర్థమైంది? As the length increases, the resistance also increases. But what about when we have a thick wire, the resistance decreases. That means if area of cross section is large, the resistance decreases, and the resistance increases when the area is thin. But if the area is the length is large, then resistance increases. If the length is small, the resistance decreases. So the resistivity of various metals చూసుకున్నట్లయితే The materials with high resistivity means it has got high resistance and will resist the flow of electrons. A material with low resistivity means it has low resistance and thus the electrons flow smoothly through the material. Okay, so the material with high resistivity means it has got high resistance and will resist the flow of electrons. A material with low resistivity means it has low resistance and thus electrons flow smoothly through the material. Right. So, resistance and conductance are inversely proportional, children. That's why what he gave here, the material with high resistivity means it has got high resistance and will resist the flow of electrons. A material with low resistivity means it has low resistance and thus the electrons flow smoothly through the materials. For example, copper and aluminum have low resistivity. Copper has low resistivity, aluminum has low resistivity. Good conductors have less resistivity. Insulators have high resistivity. So the resistivity of semiconductor lies between the conductor and insulator. So this is to be noted. Very important point. The resistivity of semiconductor lies between the conductors and insulator. Gold is a good conductor of electricity and so it has low resistivity. Gold has a very low resistivity, children, and it is a good conductor. Gold is a very good conductor. So therefore, uh, copper and aluminum have low resistivity. Good conductors have less resistivity. Insulators have high resistivity. So the resistivity of semiconductor lies between the conductors and insulators. Gold is a good conductor of electricity and so it has low resistivity. And the temperature coefficient of resistance we have to study, but the many things are there here, children, to say. uh, what more I can say, many examples for uh, various resistors or good conductors have low resistance. Iron, nickel has a low resistance because they are good conductors. Copper and aluminum have low resistivity, so that's why they are good conductors. So good conductors have less resistivity. So copper, aluminum, iron, okay, uh, gold, these are all low resistive elements or components or materials where the electricity can be flown very easily. ఎలక్ట్రిసిటీ చాలా ఈజీగా దాంట్లో పోతూ ఉంటుంది. Now, and flow of electricity will be very easy in conductors. The elements or materials with low resistance, low resistivity will have high conductivity. Now, for example, here the resistivity of various materials. The materials with high resistivity means it has got high resistance and will resist the flow of electrons. A material with the low resistivity means it has low resistance and thus the electrons flow smoothly through the material. Copper and aluminum have low resistivity. Good conductors have less resistivity. Insulators have high resistivity. The resistivity of semiconductor lies between conductors and insulators. Gold is good conductor and electricity, so it has low resistivity. Now coming to temperature coefficient of resistance. Temperature coefficient of resistance. Yeah. The temperature coefficient of resistance is the measure of change in electrical resistance of any substance per degree of temperature. ఏమంటాడంటే the temperature coefficient of resistance is the measure of change in electrical resistance of any substance per degree of temperature change. Measure of change in electrical resistance of any substance per degree of temperature change. So as the temperature change, how the resistance is measured. Okay. So, for example, let us take a conductor having a resistance of R naught at 0 degrees centigrade, RT at T degrees centigrade respectively. From the equation of resistance variation with temperature we get. So, this alpha naught is called temperature coefficient of resistance of that substance at 0 degrees centigrade. Temperature coefficient of resistance is the measure of change in electrical resistance of any substance per degree of temperature change. So let us take the conductor having the resistance of R naught at 0 degrees centigrade and RT at T degrees centigrade respectively. From the equation of resistance variation, I can write that RT is equal to T naught plus T and R0 is equal to T naught plus 0, right? Then RT by R naught is equal to T naught plus T by T naught plus 0. Then from this I can write RT is equal to R naught into 0 plus R naught into T by T naught. RT is equal to R naught plus R naught into T by T naught. And RT minus R naught is equal to delta R. Delta R is equal to 1 by T naught into R naught into T. That is equal to alpha naught R naught T. So what is alpha naught here? Alpha naught is equal to 1 by T naught. So this T is equal to temperature coefficient. T is equal to alpha naught into, you remember here, let us take a conductor having a resistance of R naught at 0 degrees centigrade, RT at T degrees centigrade respectively. From the equation of resistance variation with temperature, we have alpha naught is called temperature coefficient of resistance of that substance at 0 degrees centigrade. RT by R naught is equal to T naught plus T by T naught plus 0. RT is equal to R naught plus R naught into T by T naught. RT minus R naught is equal to del R, that is equal to 1 by T naught into R naught into T. అంటే alpha naught into R naught into T, where alpha naught is equal to 1 by T naught. This they remember point. ఇది గుర్తుపెట్టుకోవాలి, right? You see this figure or expression in many books you can find this RT by R naught is equal to how much అనేది. And from this relation ఏముంది, RT minus R naught or delta R, change in resistance, delta R is equal to 1 by T naught R naught into T. ఆ డెల్టా నాట్ వాల్యూ వస్తుంది మనకు, ఓకే. అండ్ ఏ నాట్ ఆల్ఫా నాట్ ఆర్ నాట్ ఇంటూ టీ, వేర్ ఆల్ఫా నాట్ ఈజ్ ఈక్వల్ టు 1 బై టీ నాట్. ఈ ఫిగర్ గుర్తుపెట్టుకోవాలి మీరు. దిస్ స్లైడ్ ఈజ్ వెరీ వెరీ ఇంపార్టెంట్ చిల్డ్రన్, ఓకే. So RT by R naught is equal to T naught plus T by T naught plus 0. RT is equal to R naught plus R naught by T naught into T. RT minus R naught, difference in the temperature resistance at temperature T and resistance at 0 degree centigrade is equal to delta R అనుకుంటే 1 by T naught into R naught into T, where 1 by T naught is equal to alpha naught. I can write 1 by T naught is called ఆల్ఫా నాట్, ఇలా రాయొచ్చు మనం. 1 by T naught is equal to ఆల్ఫా నాట్ అని రాసుకోవచ్చు, ఓకే. నా టెంపరేచర్ కోఎఫిషియంట్ ఆఫ్ రెసిస్టెన్స్, ఈ ఫిగర్ చూసుకోండి, ఓకే. RT minus R naught is equal to del R, that is equal to 1 by T naught into R naught into T, right? దిస్ యూ హ్యావ్ టు నోట్ డౌన్ చిల్డ్రన్. ఇది మీరు నోట్ డౌన్ చేసుకోవాలి. RT by R naught is equal to. Okay. Now, from the above equation, it is clear that the change in electrical resistance of any substance due to temperature mainly depends upon the three factors: the value of resistance at the initial temperature, the rise of temperature, and the temperature coefficient of resistance alpha naught. The value of resistance at initial temperature, the rise of temperature, and the temperature coefficient of resistance alpha naught. The value of resistance at initial temperature, the rise of temperature, and the temperature coefficient of resistance alpha naught. RT by R naught is equal to T naught plus T by T naught plus 0. RT is equal to R naught plus R naught into T by T naught. RT minus R naught is equal to delta R 1 by T naught into R naught into T, or alpha naught into R naught into T, or where alpha naught is equal to 1 by T naught. Alpha naught is equal to 1 by T naught. So from this above equation, it is clear that the change in electrical resistance of any substance due to temperature is mainly depends on three factors: the value of resistance at initial temperature, the rise of temperature, and the temperature coefficient of resistance alpha naught. This alpha naught is different for uh, this alpha naught is different for different materials. So effect on resistance at different temperature are different in different materials. This అంటే వేరే వేరే మెటీరియల్స్కి, వేరే వేరే మెటీరియల్స్కి కండక్టింగ్ మెటీరియల్స్కి ద ఆల్ఫా నాట్ ఈజ్ డిఫరెంట్. ఫర్ ఆల్ఫా నాట్ ఈజ్ నథింగ్ బట్ టెంపరేచర్ కోఎఫిషియంట్ ఆఫ్ రెసిస్టెన్స్. సో దిస్ టెంపరేచర్ కోఎఫిషియంట్ ఆఫ్ రెసిస్టెన్స్ ఈజ్ different for different material. So effect on resistance at different temperature are different in different material. So the temperature coefficient of resistance at 0 degrees centigrade of any substance is the reciprocal of inferred zero resistance temperature of that substance. So far we have discussed the materials that resistance increase with increase in temperature, but there are many materials electrical resistance of which decreases with decrease in temperature. Okay. So the temperature coefficient of resistance at 0 degrees centigrade of any substance is a reciprocal of the inverse zero resistance temperature with increase in temperature. But there are many materials electrical resistance of which decrease with a decrease in temperature. Now you can see this resistance change with change in temperature. How the resistance, one you take at 0 degrees centigrade, and after T degrees centigrade the resistance will be RT. In the first line, first arrow, at 0 degrees centigrade the resistance is R naught. After some times, as the temperature increases, then T resistance temperature coefficient TT also increases. After decreasing at minus T degrees centigrade, it will below to RT minus RT naught. The resistance changes with change in temperature. So this figure is very very important, you can understand. Temperature coefficient at 0 degrees centigrade of any substance is the reciprocal of the inferred zero resistance temperature of that substance. So far we have discussed the materials that resistance increases with increase in temperature, but there are many materials electrical resistance of which decrease with decrease in temperature. Okay, so this is the figure you can understand here. Okay. 3 degrees centigrade. Now this graph, you check it, or once you draw that graph, note down చేసుకోండి. Now, actually, in metals, if the temperature increases, the random motion of free electrons and interatomic substance decreases. చూడండి, the value of resistance at the initial temperature, the rise of temperature, and the temperature coefficient of resistance alpha naught. This alpha naught is different for different material. So effect on resistance at different temperature are different at different material. Temperature coefficient of resistance at 0 degrees centigrade of any substance is the reciprocal of the inferred zero resistance temperature of that substance. So far we have discussed the materials that resistance increases with increase in temperature, but there are many materials electrical resistance of which decreases with decrease in temperature. Actually, in metals, if the temperature increases, the random motion of free electrons and interatomic vibrations inside the metal increases with result in more collisions. But more collisions resist the smooth flow of electrons through the metals. I repeat this statement. This paragraph is very important, student. Actually, in metals, if the temperature increases, the random motion of free electrons and interatomic vibrations inside the metal increases, which result in more collisions. More collisions resist the smooth flow of electrons uh, through the metals. Hence, the resistance of the metal increases with the rise in temperature. So, we uh, consider the temperature coefficient of resistance is positive for metal. ఏమవుతుంది ఇక్కడ అంటే ఇన్ దిస్ మెటల్స్ జనరలీ ద ఎలక్ట్రాన్స్ ఆర్ ఫ్రీ అండ్ డ్యూ టు దర్ మొబిలిటీ, random mobility, the collision is large. So due to that collision, okay, hmm. So more collision resists the smooth flow of electrons through the metals. Hence, the resistance of the metal increases with the rising temperature. So we consider the temperature coefficient of resistance as a positive, children. Okay. Now, power auto off. But in case of semiconductors, or other non-metals, the number of free electrons increase with increase in temperature. So the random motion of free electrons and interatomic vibrations inside the metal increases. But in case of semiconductor or the other non-metals, the number of free electrons increases with increase in temperature, because at higher temperature, ha, padali. So at the higher temperature, generally what happens, uh, due to the sufficient heat energy supplied to the crystal, a significant numbers of electrons come into the conduction bands from the valence band, uh, increase the resistance of this type of non-metals substances decreases with increase in temperature. Hence, temperature coefficient of resistance is negative for non-metallic substances and semiconductors. So, temperature coefficient of resistance is positive in case of conductors, but in case of semiconductors and non-metals, the temperature coefficient of resistance becomes negative, and this is the cause what happens here. Why? In semiconductors or other non-metals, the number of free electrons increase with increasing temperature, because at the higher temperature, due to the sufficient heat energy supplied to the crystal, a significant number of covalent bonds gets broken, and hence more free electrons get created. So that means if temperature increases, uh, as the number of free electrons increases, the resistance of this type of non-metallic substance decreases with an increase in temperature. Hence the temperature coefficient of resistance is negative in case of non-metallics or semiconductors, but in case of conductors, children, it is absolutely opposite to the behavior of semiconductors and non-metals, right? So in the next class we will discuss the electricity topic, other topics. Okay, so this is the first class in electricity, I think. Next time we will go with another new topic, children, right? So see you. Bye. I'll conclude here. Okay.